Good afternoon. Welcome to week 6 problem solving sessions on the course on regression analysis, and today we'll be talking about week concepts discussed during week 4 lectures and solve a few problems related to it. So without any further ado, let's get started. Alright, so before venturing into week 6 concepts, let us just run through what we have learned so far. So yes, so far we know how to fit a linear regression, we know how to fit a multiple linear regression, we know what the aim is, that is to minimize the residual sum of squares. We know the technique, like we just have to write down the residual sum of squares and then differentiate with respect to the unknown parameters, equate them to 0, and then solve the simultaneous equations, set of equations, and arrive at the regression coefficients. We also learned about the properties of the regression coefficient, that is, it is unbiased and it's normally distributed with some mean and some variance, right? And also we learned how to test for significance of the entire regression model, that would be an F test, or we have learned how to test uh, for a hypothesis for a subset of regression coefficients. So we could, if we have one variable to test, then we can go ahead with the t-test. If we have more than one, then we can go ahead with the f-test using the extra sum of squares techniques. And we've learned how to create confidence intervals and arrive at prediction intervals. And then during week 4 and 5, during the last 2 weeks, we learned how to go ahead with variable selection. Okay, so there are two ways primarily by which we can do variable selection. The first one is that we fit all possible regressions and then we evaluate each of them, or we group them into a number of predictors that we are using. We evaluate each of these group with respect to these matrices, or in other words, we evaluate all possible regressions in terms of these matrices: R square, adjusted R square, MS residual, and malus CP, and then we take a decision as to which model to go ahead with, right? This is one of the major techniques of variable selection. Yesterday we learned about some other ways of variable selection, or rather I would say model selection, okay, and that was sequential selection. So in sequential selection, yesterday we learned about forward, uh, backward, and stepwise. So what happens in case of forward regression? Forward regression is that we find out significant predictors and then keep on adding to the model until and unless there are no more significant predictors that can be added to the model. Okay, sorry. Sorry about that. Then we learned about backward model selection. This is just the opposite of forward selection. So what happens in forward selection? We keep on adding variables which are significant given the previously added uh, predictors, okay, and then we try to evaluate that given the set of existing predictors, what more what more of the variance in y can be explained by addition of this new predictor. Okay, in case of backward selection, what happens is that we fit the full model, we take all possible predictors, fit the model, and then we drop it one by one. We drop it sequentially such that the least significant predictor gets dropped first, and then the next least significant predictor gets dropped, and so on and so forth. All right. And in case of stepwise um, regression, uh, yeah, sorry about that. I got logged out, so I'm going to start all over. I don't know till what time it was there. Yeah, so we learn yes, so we were talking about sequential selection. It could be forward, it could be backward, it could be even stepwise. Okay. And yes, and it could be forward, it could be backward, it could be stepwise. So what happens in stepwise regression is that we go back and forth. We first fit, like in the first step we take the most significant regressor, then we add the next most significant, and then we I mean in the second step we try to add the next most significant, given that we have already added the first one, and then we check whether the first one remains significant after the addition of the second parameter, second regressor as well. All right. So this is the thing that we do even after incorporating one regressor in the model. We don't completely forget about it. We go back and forth and we check that each and every regressor in our model, we check until each and every regressor in our model remains significant. Besides the fact that the model remains significant or not, we also, that is something we don't usually check. I mean, that is not something we check, that if the model on the whole remains significant, but for a good model this also should hold, right? So yeah, so sequential selection, forward, backward, we have learned. And then in stepwise, what we do, we keep on adding variables and check whether the previously added ones continue to remain significant until and unless all the regressors in the model are significant. Okay, so these are some of the techniques. Yeah, so these are some of the techniques that we learned. And then this week, in week 6, we talked a lot about multicollinearity. Okay, and today I'll be explaining what do we actually mean by multicollinearity, what are the problems associated with it, and how to work around problems of multicollinearity, and then we'll solve a few problems to get a better hang of it, right? So first things first, what do we mean by multicollinearity? So multicollinearity happens when this occurs when two or more regressors are highly linearly dependent. Okay, so this linear dependency is something that we have to keep in mind. Okay, yeah, so what is the problem? Why do we try to address this? even if it is multicollinearity, even if multicollinearity exists, why is there a need to tackle this? So for this I am going to write down something over here. Okay, so let's say we have multicollinearity problem. So we have x1, x2, x3. Okay, and this is the intercept term. Okay, 1 1 1 1 something, right? And here we have 2 4 7 9. Here we have, let's say, 5 6 2 1. And then here we have, let's say, 3.5 5 4.5 5. All right, so if we look carefully, then we can see that x3 is actually x1 plus x2 by 2. Okay, so there is a perfect linear relationship between x1 and x1 x3 or x2 x3. Okay, now if we, so to get the estimate beta hat, we have to take x prime x inverse x prime y. Alright, so now since this is my x matrix, okay, rank of x prime x will also be equal to rank of x. Alright, and this, for this to have a unique solution, rank of x should be equal to p, where p is the number of unknown parameters. Okay, so in this case, rank of x should be ideally equal to 4 in order, or I shouldn't say ideally, in order, so it should be equal to 4 to have a unique x prime x inverse. Okay, but here, since we have this linear dependency, in this case rank of x will be 3, which is less than p. So then this thing beta hat will not be unique. Okay, or in other words, we cannot perform this inverse thing. Okay, because you will not get a, I mean, we won't be able to perform this inverse thing. All right, fine. So since this won't be possible, it is very important, and also because there are some other, so this is a case when we have perfect dependency. All right, this is a case where we have perfect dependency. Now this is the case where we absolutely cannot perform this inverse operation. Now what happens if there is not a perfect dependency? Let's say we have a near perfect dependency, and when I'm talking about dependency, I'm always talking about a linear dependency. Okay, now let's say if it is something like this, that we have this x that we were talking about, and let's say correlation between x1 and x2 is not equal to 1, but it is approximately very high, let's say 0.9. So this is very high. All right, so in this case x transpose x inverse is still possible. but why don't we do it? Okay, so this is still possible, but why don't we do it? This is because if we do go ahead with a normal estimation process, then several other problems could crop up, right? So that's the thing. So what are the problems associated with this thing? So these are actually essentially the problems that can arise. All right. Yeah. So the problems are, number one, we can have large variance and covariances of regressors. Now, why do we worry about large variance? This is something which is unwanted in any kind of estimation. Why? Because let's say we are doing some sort of an estimation of a population parameter. Okay, so we want to be precise. Okay, if let's say this is my true population parameter, we want to be very, we want to go as close to this point as possible. Now if the variance of our regressors, if the variance of our estimators are very large, then there will be a lot of fluctuation. It can be here, it can be here, it can be here, it can be here. So trying to have a, so if the goal or the aim, let's say this one is the true, okay, so the goal and aim is to have a precise estimate. So precision is inversely related with variance. All right, so if we want to have a very very precise estimate, we have to ensure that the variance of our regressors are low. Okay, but this usually doesn't happen when we have multicollinearity in the data set. All right, so this is one problem that uh, that is absolutely unwanted, and we don't want to do that. Okay, and so how in order to find out this large variance, what is it that we have to do? So first we have to um I mean first we have to learn how to estimate in 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 the presence of multicollinearity. So how do we do that? So first things first, we if we have, let's say, something like this, um, y equal to beta naught plus beta 1 x1 plus beta 2 x2 plus epsilon. So let's say this is our model in hand. All right, I equal to 1 to n. Okay, and then the if the model matrix or the x matrix will be this thing, it will be 1 1 1 1 1. Then we'll have x11, x21, x31 and xn1, and we also have x21, x22, x sorry, it will be x12, x22, x32 and so on till xn2. Okay, so sorry, so this is the model matrix. So step 1 is centering and scaling the data, scaling the X matrix and Y. Okay, so how do we do that? First, we define variables like this, that xi1 will be xi1 minus x1 bar by root over s11, where s11 is equal to summation I equal to 1 to n xi1 minus x1 bar whole square. Okay, and similarly we'll do xi2 equal to xi2 minus x2 bar by root over s22, where s22 is summation I equal to 1 to n xi2 minus x2 bar whole square. Okay, and yi is yi minus y bar by root over syy, whereas syy is summation I equal to 1 to n yi minus y bar whole square. Alright, and x1 bar, I'll write it here. So x1 bar is summation I equal to 1 to n 1 by n x I1. Okay, similarly we'll have x2 bar equal to 1 by n summation I equal to 1 to n xi2. Okay, and finally y bar is summation yi by n. Alright, so now that we have centered it about mean, and divided it by root over s11, what do we see? Since we have centered it by mean, we can find that x1 bar will be 0, x2 bar is also 0, okay, and y bar is also 0. Okay, so notationally, let me write this. This is xi1. Okay, so xi bar, x1 bar is this thing, and let me just write it in a different way to keep parity. I'll write it like capital X1 bar. Okay, this is capital X2 bar and this is capital Y bar. Alright, and here we have small x1 bar like this. Similarly, we'll have capital X1 bar. Okay, so capital X1 bar will be summation 1 by n summation xi1. Alright, so let me just write it in a different way. I'll write these as capital X's, so then I don't think there'll be any more confusion. Okay, so this, let it be capital X11, capital X21, capital X31, capital Xn1, capital X12, capital X22, capital X32, and so on, capital Xn2. Alright, so here we have xi1 as capital xi1 minus x1 bar by s11. xi2 bar will be capital xi2 minus x2 bar by root over s22. Okay, and s11 will be this. Oh, here I've written capital already. Yeah, this is this, this is this, and we have this thing. Okay, so capital X1 bar is 1 by n summation capital Xi1, and capital X2 bar is similarly 1 by n summation Xi2. Alright, so now that we have centered it about mean, then small x1 bar will be 0, small x2 bar will be 0, and y bar there will also be 0. So the smaller ones, smaller xy, and so these variables lowercase x1, x2 and y, these are actually mean centered. Alright, so if I do a summation xi1 square, I would get 1. If I do a xi2 square would be 1, and summation yi square will also be 1. Alright, now, so then we are going to fit the model assuming that these xi, x1, x2, y are mean centered and scaled. Okay, so now then the model becomes yi equal to beta naught plus beta 1 xi1 plus beta 2 xi2 plus epsilon I equal to 1 to n. Okay, so initially we were fitting a model with the capital X's with these variables. Now after doing this centering, this mean centering, and then we are fitting with the smaller x's. Alright, now in this scenario, what do we have? We have that beta naught hat in this case will be how much? This will be y bar minus beta 1 hat x1 bar minus beta 2 hat x2 bar, and that would be 0 since all of these become 0. Alright, so since beta naught hat becomes 0, then we have a reduced X matrix, which is nothing but we can just do away with in this sort of a situation. Beta naught will always be 0. Okay, so that estimate since is 0, we can simply do away with the intercept term and then fit a linear model with only these two x terms. Okay, so then what do we have? We have here x11, x12, x21, x22, and then we have xn1, and then we have xn2. So this is my revised model matrix. Is it okay? Now, since we have this and y also will be now, so I'll name it as x star and this will be y star. Y would be y1 to yn. Alright, so then now we'll have our normal equation as x star prime x star inverse x star prime y star. Okay, that would give me beta hat. Alright, now x star prime x star would be actually, this is actually 1 r12 r121 inverse into r1y R2y. Alright. Okay. Now where R12 is summation xi1 xi2. Mind you, small xi bar and x2 bar are 0. So this is actually the correlation, and divided by the root over xi1 square, xi1, that is the variance of, this would be, this is covariance divided by variance, right? So the down part is always 1. So R12 will become xi1 and summation xi1 xi2. Alright. And R1y is nothing but summation xi1 yi. R2y is actually summation xi2 yi. Alright. Only the cross product terms. So then if we invert this thing, then what do we have? We have here, so we have to find out the determinant. So A inverse is, one second, yeah. So here any model A inverse is adjoint of A by determinant of A. By that logic, x star prime x star inverse would be, so determinant is 1 by 1 minus R12 square. Okay, so this will be 1, this will be minus R12 by 1 minus R12 square, and this is again 1 by 1 minus R12 square. Alright, so then beta hat would be this matrix as above into R1y and R2y. Okay, so if we multiply this by this, then what do we get? We'll finally land up here. So we'll have R1y, so we'll have beta 1 hat as R1y minus R1 to R1 to R2y, this is this thing, R1 to R2y divided by 1 minus R12 whole square. Similarly, beta 2 hat will be R2y minus R12 or 21, I'll write as 12 because it's the same thing, R1y by 1 minus R12 square. Okay, now variance of beta 1 hat in that case would be sigma square x star prime x inverse 1 1th element. Okay, so then that will be sigma square by 1 minus R12 square. And variance of B2 hat is also the same thing, sigma square x star prime x star inverse their 2 2th element. So that is also sigma square by 1 minus R12 star. Now note, as R12 goes to 1, this denominators, this one and this one, they will move closer to 0. Okay, so if this happens, then variance as a whole will tend towards infinity. Alright, so this is the problem that we was referring to earlier. Okay, the variances of the estimators in the presence of multicollinearity, they will shoot up and we will not get precise estimates. Alright, I'm sorry. And then we were also talking about the covariances, right? So if I want to find out the covariance between beta 1 hat and beta 2 hat, then that is sigma square r12 by 1 minus r12 square. Okay, because that will be actually sigma square x star prime x star inverses 1/2th element. So essentially it will be this element. Okay, minus r12 by 1 minus r12 square. Here again, if r12 is going towards infinity, then this part will go towards 0 and this part will also, the denominator will also go towards 0 at a faster rate than the numerator. As a result, what will happen? This entire thing will also shoot up to infinity as r12 goes to 1. Okay, so this denominator will go close to 0 and this will shoot up to infinity. Okay, sorry, there should be a minus sign over here. So then the covariance can go to plus minus infinity depending on whether r12 is positive or r12 is negative. But in either cases, even if it is highly, strongly linearly related, then these covariances will also shoot up. Okay, this was one of the problems that we were talking about. Okay, the least square, if the variance is large, then as a consequence what happens, the least square estimates of regression too far from the true parameter. Okay, and there could be a reversal in the direction of effect as well. Okay, and the next thing is that if we do have multicollinearity, then there are chances that the global test is significant but partial tests are not. Okay, and then the chances of getting a different model from different model selection techniques also get higher. Okay, so this is the thing. Let's say we have the least square estimate as beta hat. Okay, so if we have multicollinearity problem, then beta hat is, as I said, too far from actual beta. Okay, if we have to quantify this far, then we can think about the squared distance. Okay, that if I write as L square, that is summation I equal to 1 to k minus 1. Okay, because let's say we have k minus 1 regressors. Okay, model is beta naught plus beta 1 x1 plus beta k minus 1 xk minus 1 plus epsilon. Let this be the model. Okay, and we have k minus 1 regressors. We want to find out the squared distance from the actual ones. So this one will be beta I hat minus beta I whole square. Alright, so we can find out that expectation of L square will be equal to summation I equal to 1 to k minus 1 sigma square by 1 minus ri square. Okay, this is already shown in lecture. Fine. So now what happens is that, what is ri? Ri is the coefficient of multiple determination, that is r square, capital R square, when we regress xi on remaining xk minus 1, or I'd rather say on remaining k minus remaining among k minus 1 variables or regressors. Alright, now what happens is that if ri square goes to 1, then this thing, expectation of L square, is large. Okay, so then if L square, or expected value of L square, is large, it means that these estimates are too far from our actual estimates. Okay, another thing that could go wrong that we've already discussed is that we are expecting some positive sign, but then the betas become negative. Okay, this reversal in the direction of effect could also happen. Okay, and there could also be a situation where we have the global test as highly significant, but the partial tests are the partial tests are insignificant. Okay, and different model selection techniques will yield different models in the there will be marked differences in the model selection if we have severe multicollinearity problems in the data set. So these were the problems associated with multicollinearity. Now what can we do about it? How can we? First is, before diagnosis, before before tackling, there should be detection. Okay, and how do I detect that? We can use different techniques. So these are some of the techniques. So before even tackling, we should be able to detect that there is a problem. Only after detection and acceptance that okay, there is a problem, we'll be able to solve it. So the first method is to examine the x cross x matrix for two regressors. Okay, so if in the previous case that we have seen, x prime x, that matrix, if we know that R12 is greater than, let's say, 0.8 or 0.9, then we know that x1 and x2 are highly linearly dependent. Okay, so in this case, for a two regressor model, this method fares well. Okay, but if we have greater than, so this is for two regressors, but for greater than 2 regressors we have to opt for some other techniques. Okay, so the first thing is this: we could use condition number. Now how do we get condition number? So then what do? We take x prime x matrix, okay, or rather x star prime x star, the mean and mean centered and sort of standardized matrix, and then we find out the eigenvalues of this matrix. Okay, so if we have k minus 1 regressors, this one will be a k minus 1 cross k minus 1 matrix. Okay, and this will also have k minus 1 eigenvalues because it will be full rank, right? So then we will have lambda 1 to lambda k minus 1 as our k minus 1 eigenvalues. Alright, so since small eigenvalues, small lambdas, indicate that linear dependence among regressor. Okay, so then the condition number will be maximum of these lambda i's by minimum of these lambda i's. Okay, and the rule is this: if Cn is lesser than 100, there is no serious problem. If Cn is greater than 1000, then there is a severe problem, and anything between 100 to 1000, it is said that it's a moderate to strong multicollinearity problem. Okay, so this is the condition number or condition index, or this is condition number, and condition index is actually max of lambda I by lambda I. So condition index we have to find for each I, and then the largest condition index is the condition number. Okay, so max of condition index I is actually my condition number. Okay, so if lambda I, any lambda I, if it is close to 0, then the associated eigenvector, it describes the nature of linear dependence. Alright, now the next thing that we can use for detection is the VIF, or the variable inflation factor. How do we find this out? Variable inflation factor is by, first is we regress xi on the other, let's say k minus 2 regressors. Okay, and get the Ri square from that equation. Ri square is the coefficient of determination. Alright, and then if we find out the VIF, which is VIF I is 1 by 1 minus Ri square. Okay, so in that case, if Ri square is high, VIF is the this will shoot up, and this is associated with the variance of the betas. So the variance of the betas will shoot up by this number. Okay, why? Because if you remember, this thing, variance of bi hat was actually sigma square by 1 minus Ri square. Okay, why? Because this was sigma square x transpose x inverse, x star transpose x star inverse their ith element. Okay, and we saw from here, from the two variable situation, that these off diagonals are actually this will, in case of these variables, it would be so variance of bi hat is sigma square by 1 minus Ri square, which is nothing but sigma square x transpose x inverse and their ith element. Okay, of that regression model where so VIFI is 1 by 1 minus Ri square, where, and this is the variable inflation factor, because the variance of beta I, it gets sigma square is getting inflated by 1 by 1 minus Ri square. Okay, so then this will go to infinity as Ri square tends to 1. Okay, and the general rule is that VIF greater than 5 is suspicious and VIF greater than 10 is most certainly. So VIFI greater than 5 we should suspect, and VIFI greater than 10 is indicative of presence. Okay, and is most certainly a problem. Alright, so now how do we tackle this? How do we how do we correct multicollinearity? We could collect additional data, because remember, multicollinearity is actually a sample phenomenon. Okay, it might happen, it may not happen, because usually in most cases we will not have um, perfect linear dependency we would have, we'll have, because we usually have near perfect dependency if we don't get samples which are too, um what do I say, uh, if samples don't come up which reflect the actual underlying linear dependency, then we won't be having this multicollinearity problem. So it is always a sample phenomena. So one way to check this is to collect additional data. All right, so that this will actually break the existing multicollinearity. Okay, so if by chance, let's say, there is no underlying multicollinearity, but just by the virtue of the sample it looks like it is multicollinear, so if we get additional data points into the system, then we can break that seemingly multicollinear behavior between the two regressors, and then proceed with normal OLS estimation as well. Okay, so one good way is to, if possible, if cost and time and other things permit, then we should definitely we can collect additional data to, you know get a workaround this problem. All right, the next thing is that, very simple, whichever is creating issues, just remove them. Okay, so removing regressors is another issue. So, and then if we want to remove it, then we have to pick and choose which to remove. Okay, so we use our own judgment and discretion. Okay, but elimination is, um it is helpful. How helpful is it? We are not so sure. Will it retain predictive power? We are not so sure. So these are some of the um, criteria, or rather concern, that one can have while removing regressors. We just can't randomly remove and then magically hope that the model will perform better. We have to be extremely cautious, take all um, possible scenarios, or I would rather say, um, we have to be very mindful that even after removal of regressors, we do land up at a model that predicts well, and that can, capture the linear relationship between the regressors and the response variable. Okay, mindlessly removing regressors will reduce, or will actually harm the modeling purpose. All right, so if we have to remove regressors, we have to choose which ones to remove, after removal which ones make sense, and we cannot afford to remove like significant and very relevant variables. So yeah, so some sort of judgment and discretion is necessary if we do decide to remove regressors. All right, and then we the third thing is to collapse. Okay, what do I mean by collapse? We mean that we combine two or more variables which are linearly dependent into a single composite variable. Okay, and then use that instead of those to fit our model. So one of the one of the ways to collapse is to work with the principal components. Okay, so if let's say we have this, that x prime x has eigenvalues lambda 1, lambda 2, lambda k, and we devise a diagonal matrix such that these form the diagonal, and then we can decompose x prime x into v dv prime such that v prime equal to v prime equal to v prime v equal to I. So this is something which is known as spectral decomposition. Okay, so this entire x cross x, k cross k matrix can be decomposed into v dv prime. Alright, so then what do we have? So then we can write this y equal to x beta plus epsilon as y equal to x, since v prime is an orthogonal matrix, v prime beta, okay, plus epsilon. We can write it like this way. Then we have xv this one, if we write it as z, some other variable, some transformed variable, and v prime beta would become, let's say, alpha plus epsilon. Okay, then we can find out alpha hat as z prime z inverse z prime y. Okay, and z prime z inverse would be xv prime xv inverse. Okay, so this would be v prime x prime x v inverse. So then this x prime x, we can write it as v prime. Here we have written it, we have decomposed x prime x into vd v prime. So v prime v d v prime v inverse. So then v prime v is actually I because it's orthogonal, and here also v prime v is I. So ultimately we land up at d inverse. Alright, so this one alpha hat actually then becomes d inverse z prime y. Alright, and then variance of alpha becomes what? It becomes d inverse z prime, variance of y is sigma square I into d inverse z transpose. Okay, so this then becomes d inverse z sigma square and then z prime, again d inverse. Now z prime is d, so this would be sigma square d inverse d the inverse, this is I, so we ultimately have sigma square D inverse, which is sigma square 1 by lambda 1 to 1 by lambda k. So then elimination of one or more principal components associated with smallest eigen values will reduce multicollinearity. Okay. So then instead of using all k variables, we can use instead of using the k regressors, we can plan to use the top 2-3 principal components, and then that would take care of the multicollinearity problem here. Fine. So with that, let us proceed to a few problem solving things, and then we can finally complete week 6 sessions. Alright, so this is the first one. Consider a multiple linear regression model with k-1 regressor variables if there is a strong multicollinearity between xj and any subset of the other k-2 regressors. Variance of beta hat will tend to how much? So variance of beta hat is sigma square by 1 minus rj square. So since there is strong multicollinearity between xj and any other subset, this rj square will go up to 1. So then this denominator will go towards 0 and variance of beta hat will shoot up to infinity. So that is the answer. Alright, moving on. The next thing is, can we use this data to get a unique fit to the model? So how do we do it? Let us first find out if there exists any dependency between x1, x2 and x3. Okay, so if we look carefully, x1 is actually x2 plus x3 by 2. Okay, 4 minus 2 by 2, 1. 11 minus 7, 4 by 2, 2. 8 by 2, 4. 14 by 2, 7. 16 by 2, 8. So this is a perfect linear relationship. So therefore, we won't be able to find out x prime x inverse, and therefore we won't be able to get a unique fit. So the answer is no, B. Fine, moving on. So they have asked us to consider this model, y equal to beta naught plus beta 1 x1 plus beta 2 x2 plus epsilon. Center and scale the x1, x2 and y columns. Let x1, x2, y be centered and scaled columns, small x1, small x2, xy. And now we have to fit this model. What is the least square estimate of beta 1? So let us just try to do this. x1, x2, y. So here we just find out x1 bar, x2 bar and y bar. Okay, let us find this out first. So x1 bar is how much? Minus 3 plus 3 by 5, that is 0. x2 bar is how much? Minus 5 plus 5, 0. Y bar is how much? Y bar is 12 plus 18, 30 plus 14, 44 plus 60, 50 by 5, that is 10. Alright. So then x1 is how much? Okay. So S11 is how much? S11 is summation x1 I minus x1 bar whole square. So this x1 bar is 0. So this is sum of squares. So S11 will be 4 plus 1, 5 plus 1, 6 plus 4, that is 10. Similarly, S22 is how much? This is summation x2I minus x2 bar whole square. So this one will be again summation x2I square, like this one summation x1I square. So then this will be 4, 16 plus 1, 17 plus 17. So that will be 34. Okay, and this thing, so S11 is this, S22 is this. Now we have to find out SYY. So this is actually y bar, we have to find out. This is 10. So y minus y bar is actually 2 minus 1 minus 1, 2 and then 6. So this will be 4 plus 1, 5 plus 1, 6 plus 4, 10, 16. Alright. I hope there are no calculation mistakes over here. Oh, sorry. This is actually y bar is 60 divided by 5. So y bar is actually 12. Okay. So y minus y bar is actually 0 minus 3 minus 3 2 and this is 4. So 9 plus 9, 18 plus 4, 22 plus 16 would be 38. Sorry, what did I do? SYY will be 38. Alright. So now that we have found S1, S11, S22, SYY, we'll find out x1, small x1, small x2 and small y. So I'll just pull it up from here. So this is x1, x2, xy. So I'm going to write x1, x2 and y. Alright. So x1I would be xi1 minus x1 bar by root over s11. Okay. So x1 bar is 0. So this will be, and here I have S11 is how much? I'll write it down here as well. S11 is 10. S22 is 34. And SYY is 38. So this will be minus 2 by root over 10. Okay, so then how much does this come? So minus 2 divided by square root of 10. So this is minus 0.632. This is again plus 0.632. This is minus 0.316. This is plus 0.316. Sorry, this one here is plus 0.316 and 14, sorry, this is minus 0.316. This is 0 minus 0 will be 0 and this is plus 0.316. Okay, similarly we'll find out x2. X2 will be minus 4 divided by square root of 34. So this is minus 0.686. This is plus 0.686. Then we have minus 0.7171 and plus 0.171 and this is 0. Alright, similarly, so I'll just write it in a proper manner. We just have to align it. Alright, I'll just let it be for the time being. So this is minus oh, so this is minus 0. Okay, so I'll just write it down. This is minus, I'll just align it properly, minus 0.632, then minus 0.316, 0, 0.316 and 0.632. Okay, and this is minus 0.686, minus 0.171, 0, 0.171 and 0.686. Okay, and similarly y bar will be how much? Y is equal to, okay, y bar is 12, so this will be 12 minus 12, 0. Okay, and then we'll have 9 minus 12, that is minus 3, divided by square root of 38. So that will be minus 3 divided by square root of 38. So this is minus 0.487. Okay, this is 0.487. Then we have 2 by this thing, so it will be 2 by this thing, that is 0.324, and then we'll have 4 by root over 38, that would be 0.649. all right, so this is actually the mean centered and transform variable. Okay, now we, from the previous exercise, we have seen that whenever we are doing this mean centering, since beta naught hat estimates comes out to be 0, we are removing the intercept from that model and we are fitting y equal to beta 1 x1 plus beta 2 x2 plus epsilon. We are doing away with the intercept term in this way. So then the usual way to get beta 1 beta 2 is to write down this thing, summation y I minus beta 1 x1 minus beta 2 x2 whole square. Okay, so this is sum of squares due to residual. Now we are going to differentiate del s by del beta 1 once, equate it to 0, and then we'll find del s del beta 2, and then we'll equate it to 0, and then we solve this system of simultaneous equations and get to beta 1 and beta 2 hat. Okay, so let us just finish this. So SS again, so this thing SS is summation yi minus beta 1 x1i minus beta 2 x2i whole square. So del of SS by del beta 1 equals 0 implies summation 2 yi minus beta 1 x1i minus beta 2 x2i into x1i into minus 1 equal to 0. So we can write it like summation yi x1i minus beta 1 summation x1i square minus beta 2 summation x1i x2i equal to 0. Okay, and del SS by del beta 2 equal to 0 implies summation 2 yi minus beta 1 x1i minus beta 2 x2i into minus x2i equal to 0, which implies summation xyi x2i minus beta 1 summation x1i x2i minus beta 2 summation x2i square equal to 0. Okay, now we'll just compute these and fill in, and then we'll have two equations. We can solve beta 1 and beta 2 from there. So let me come here. Okay, so all right, now what do we need? We need yi x1i, yi x2i, x1i square and x1 x2i. Okay, so let us just find out. This is x1 x2, this is x1y, this is x2y. Anything else we need? Oh, x1 square. So these things we have to find out. Summation x1i square equal to how much? This is 0.632 into 0.632, sorry, this will be 0.632 square plus 0.316 square plus 0.316 square plus 0.632 square. So this is 0.9986. Okay, summation x2i square is equal to 0.686 square plus 0.171 square plus 0.171 square plus 0.686 square. So this is actually 0.9996, or I could just write it as 1. Okay, and x1i square, since this is mean centered, we can easily write it as 1. Okay, because there have been some issues. So yeah, we don't even need to do it. x1i square is 1, x2i square is also 1. So all we need is this, this and this. Okay, so from here we can write, so from here we can write that summation yi x1i minus beta 1 minus beta 2 summation x1i x2i x1i equal to 0, and here summation yi x2i minus beta 1 summation x1i x2i minus beta 2 equal to 0. Okay, so this is my final reduced equation. This term and this term will go to 1 because it is mean centered. Okay, so now we'll have to plug in these values. So x1 x2 is how much? X1 x2 is 0.632 into 0.686. So this is 0.434. Here again we have 0.434, and then again we have 0.316 into 0.171. So this would be 0.054, 0.054 and 0. Alright, so now we have to find out x1 prime y. So this is 0, 0. Then we have 0.316, 0.316 into 0.487. So this will be 0.154. So here this would be 0.154. This would again be 0 into 0, so 0. This would be 0.316 to 0.324. So that would be 0.316 into 0.324. That would be 0.102, and then again 0.632 into 0.649. That will be 0.632 into 0.649. So that is 0.410. Okay, and again x2y, this is 0, the third one is 0, 0.171 into 0.487. So 0.171 into 0.487, that is 0.083. And then again 0.071 into 0.324, that will be 0.171 into 0.324, that is 0.055. And then again 0.686, 0.686 into 0.649. So now then this is 0.445. Okay, now we'll take a sum of these, all of these. So sum of x1 x2 would be 0.434 plus 0.054 plus 0.054 plus 0.434. So this is 0.976. x1 prime y is how much? That is 0.154 plus 0.102 plus 0.410. So this is 0.666, and the second one is 0.083 plus 0.055 plus 0.445, that amounts to 0.583. Okay, so now coming back here, we'll have summation y1 is 0.666. So this will be 0.666 minus beta 1 minus beta 2 into, that is how much, x1 x2, 0.976, 0.976 equal to 0. And then here we'll have y1 x2, so that would be 0.583, 0.583 minus beta 1 into 0.976 minus beta 2 equal to 0. Okay, so if we solve this, let's say I'll multiply this with 0.976 and then subtract. Alright, so what will we have? This one will be 0.583 into 0.583 into 0.976 will be 0.569 minus 0.976 into 0.976 is actually 0.9 minus beta 1 0.953 minus 0.976 beta 2 equal to 0. Okay, so this minus this will cancel out beta 2, and so this is equation 1, this is equation 3. So if we do 1 minus 3, what do we have? We have 0.666 minus 0.569 minus beta 1 plus 0.953 beta 1 equal to 0. Okay, so then this will be beta 1 equal to 0.666 by 1 minus 0.953. So how much does it come to? 0.666 divided by 1 minus 0.953. So this will be something 14.17. Alright, so yeah, we'll find out whether we have this or not. Okay, no. So where is this mistake? Let us find out. Till here we are good. Yeah, so then this one into this one, 0.976 square, 0.976 square is 0.953. And 0.666 minus 0.569. Okay, I have not subtracted this. Yes, so here this will be minus 0.569. This is something I forgot to do. Okay, 0.666 minus 0.569 divided by 1 minus 0.953. Yes, this comes to 2.06. So that is actually my beta 1, 2.055. Alright, now next thing is the linear estimate of beta 2. So once we have this, beta 2 is how much? Beta 2 is, so from here, from 3, what do we have? Beta 2 is, sorry, from 2, this is equation 2. So from equation 2, we have this thing, 0.583 minus 0.976 beta 1 minus beta 2 equal to 0. So then beta 2 equal to 0.583 minus 0.976 into 2.055. So that would be 0.583 minus 0.976 into 2.055. Okay, so this is minus 1.416. All right. Okay, so this is actually minus, so I think that will be there will be a minus sign over here, and we'll have option C as the correct answer. All right, so this is a way to solve, and so we should be able to follow this way. All right, fine. So now that we are done, this is 5. So consider the data in problem 3. This is the data in problem 3, this thing. Now they are asking us to find out the variance inflation factor for the first regressor x1. So here, since we have two models, since we have two regressors, VIF1 will be equal to 1 by 1 minus R12 square. Okay, now R12 is how much? It is summation x1 x2 I by summation x1 I square summation x2 I square root. So this will be, this is 1, this is 1, this is 0.976. So therefore VIF will be 1 by 1 minus 0.976. So this will be equal to, or it the square. So that would be so this is equal to 21.086, which is greater than 10, and thus there exists multicollinearity. So this will be 21.086, which is option B is the answer. All right, moving on. So what is the value of the determinant of this correlation matrix? It is 1 minus R12 square. Okay, so this is this thing, 0.04742. Fine. Because this is 1 minus 0.976 square. If you calculate, it will come to this. Alright. Next thing is condition number k of x prime x is how much? So in order to find out condition number k, we have to first find out this thing, the eigenvalues of x prime x. So here we are going to put in the two columns of the transformed variables. Okay, so this is minus 0.632, then what do we have, minus 0.316, 0, 0.316, 0.632, and here similarly we'll have minus 0.676, 686, minus 0.171, 0, 0.171, 0.686. Okay, so x transpose, so this is x, so x transpose x will be minus 0.632 minus 0.316, 0, 0.316, 0.632, and this will be minus 0.686, minus 0.171, 0, 0.171, 0.686 into x. Okay, so this will be actually summation x1 square, this diagonal will be summation x2 square, and the off diagonals will be summation x1 x2. Alright, so we have our x matrix ready, because x prime x is summation x1 square is how much? That is 1. Okay, this is also 1, and x1 x2 summation, that boils down to 0.976. Okay, so it is 0.976, this is also 0.976. Alright, now if I have to find out eigenvalue, what do I have to do? I have to see x prime x minus lambda I determinant equated to 0. So then what happens? This is 1 minus lambda, 0.976, 0.976 determinant equal to 0. So what do we get? We get 1 minus lambda square minus 0.976 square equal to 0. Okay, so this will be 1 minus lambda minus 0.976, 1 plus lambda, 1 minus lambda, sorry, plus 0.976 equal to 0. So then 1 minus, so then from here we have alpha as 1 minus 0.976 and alpha 2 as, sorry, alpha 1 as 1 plus 0.976, alpha 2 as 1 minus 0.976. So this will be 1.976 and this is 0.024. Okay, so then what do we have to find out? We have to find out the condition number. So condition number is lambda max by lambda mean. So this is 1.976 by 0.024. So this comes to this is 82.33. Okay, so that is the answer. All right, now moving on. So consider the data in problem 3. Is there any serious problem with multicollinearity? So now this, since Cn is less than 100, we can say that no serious problem. And option is B. Okay, so with that we come to the end of today's session. Thank you so much for staying tuned, and if there is any doubt, please post it in the discussion forum and I'll see you next week. Thank you.